Hello everyone, welcome to the Easy Power webinar series. My name is Jim Chastain, I'm your host for today's session. The topic is an introduction to testing protection systems. And our guest speaker is Mr. Scott Cooper of Omicron Electronics. Before I hand the baton over to him, I had a couple of housekeeping announcements to make. First of all, everyone in attendance today will receive a certificate of attendance for the time that you've attended. Most people use that to support ECU claims. It's nothing you have to do. It will be sent out 3 to 5 days after the webinar is over. We will have a section for Q&A at the end of the presentation, but you're welcome to use the question box of the webinar controls to enter questions at any time. And for those of you that don't know, we recorded the presentation and posted it to the Easy Power website. It will probably be available early next week. And a copy of the presentation will also be downloadable from that link. And everyone will receive a notice of that posting. Now, as we are in the habit of doing, I'd like to run a couple poll questions by you to get some feedback from the audience perspective. There's no obligation or liability, strictly just trying to get your take on the topic. So the question is, how frequently should protection systems be tested? Again, you're not going to be held for any critical reason. It's just to get some feedback on your opinion. All right, looks like we're about halfway to a quorum. The question is, how frequently should protection systems be tested? Let's give this another 5 seconds. All right, thank you. Here's how folks have weighed in. All right, looks like there's some clear preferences. Thank you. And the second question is a true or false question. You should disable the multifunction relay to prevent changing settings during test. And I actually have a don't know category as well. And there's nothing wrong with not knowing. That's why you're attending the presentation. All right, looks like we're 2/3 of the way. Let's give this another 10 seconds. Thank you. Here's how folks have weighed in. Okay, I'm in the majority here of not being sure, so I'm going to be paying attention during the presentation. And then finally, how familiar are you with PRC 005? And we're expecting a full house, so by all means, if you've got questions that you want to ask, make sure you submit them relatively early. Okay, we've got a quorum here. Here's how folks have weighed in. It looks like I'm in a majority with this one too, so good. Thank you for your participation. Now I'd like to hand the baton over to Mr. Scott Cooper.
All right, good morning and good afternoon, everyone. My name is Scott Cooper. I'm an application engineer with Omicron Electronics here in North America. For those that don't know, Omicron is a pretty big supplier of protection testing equipment around the world. And we have an office where I'm actually sitting today in Houston, where we have a training center and an indoor substation and everything for conducting training. I've been with Omicron for 10 years now, and prior to Omicron, I was with another testing company for 7. Prior to that, I was with a relay manufacturer, Beckwith Electric, for 11 years. Prior to that, I did some time with electric power systems, commissioning substations, Before that, I was in school, and before that, I was a Navy nuke. So I've been in power my whole career, been in protective relaying for quite some time now. One of the challenges to giving a talk like this is really trying to come up with content that would appeal to people of widely varying experience with protection testing. As I'm sure a lot of you know, protection testing is almost a lifelong endeavor. Most people that start with protection testing at a utility, there's usually a 3 to 5 year apprenticeship training program. So it's a wide-ranging and fairly complex topic. I think it's probably quite kind of held my interest when I first tested my first relay. I really felt like I came home. But anyway, let's begin. Yeah, the page now. Nope. So, fundamental question. We think about setting up a protection testing program or starting to test relays is why test relays? And of course, most of you know the easy answer, of course, ensure the relay operates properly to maintain safety for personnel and equipment, maximize your network state availability, and well, at least since 2007 anyway, to achieve some level of regulatory compliance and avoid fines and other administrative sanctions. So that's why we test. Let's talk a little bit about how relays actually fail. And this report started some years back. Actually, this whole compliance thing really started after the 2003 Northeast blackout in the United States. Following that blackout, there were a lot of causes of everything from vegetation management to failure of situational awareness of the system operators, to improper relay settings, improper relay maintenance settings, and there were quite a laundry list of faults. And due to the very high cost of that outage and the widespread nature of that outage, from that point, FERC really treated the bulk electric system, and as FERC defines it, that's everything above 100 kV, as a national interest and even a national security interest. So FERC then delegated to NERC, the National Electrical Reliability Corporation, collection of electric utilities. NERC then implemented a number of different compliance requirements, standards for maintaining and protective relay systems. There's quite a number of standards, and for the poll question in the beginning, PRC 005, as you probably figured out, is one of those key standards. And PRC 005, it started out, of course, like most administrative initiatives, pretty simple. All the PRC 005, the initial one said was, you have to have a plan for testing your protective relay system, and you have to follow your own plan. And as simple as that sounds, utilities did a pretty bad job of it. There was actually, PRC 005 was actually the most frequently violated protection reliability standard that NERC had. And over the years, every couple of years or so, they revised the standard, and right now PRC 005-7 is coming into enforcement. And as you can probably imagine, at each step, additional requirements were added. Utilities now have to report those misoperations above 100 kV, hence this misoperation report that NERC publishes every couple of years. And I know this data is a little bit old, but the data hasn't really changed as far as the percentages hasn't really changed that much. But this is a pie chart showing the misoperations of protection systems by cause about 10 years ago, 2013, 2014. And for those of you that are in the business, this is really shouldn't come as much surprise. A full third of the reportable relay misoperations were due to incorrect settings, logic, and design errors. And then 18% are actually relay failures and malfunctions, 13% communication failures, and you can read the rest of the pie chart. So this misoperation study has really driven some of the changes to PRC 005. The picture down on the lower right was a open CT circuit failure in a protective relay. I went to investigate many years ago, actually. The fault wasn't actually at the relay where the arcing occurred. This was a generator relay, and they had did some maintenance on the excitation system. The excitation system shared a set of CTs with this particular relay. When they concluded their testing, they went and re-landed the wires off by one position on the terminal block. They restarted the machine, flashed field, put some load on, and the weakest point in the circuit was where the CT signal goes through the aluminum case. There you can see where it arced through the plastic terminal block and onto the case and set the bundle on fire. And it was quite a costly repair by the time it was all over with the machine outage and rewiring and re-relaying and all the testing and everything afterwards. But this kind of highlights the not so much the protection area failure, but the failure of a personnel. This is an as-left personnel error that caused this particular event. Breaking this same report down a little bit further, we can see how the protection device technology affects how these relays actually fail. So here, as you might expect, microprocessor relays have a much higher rate of incorrect setting, logic, and design errors than electromechanical relays. And that really shouldn't be any surprise, because the settings on microprocessor relays have steadily grown in complexity over the years, and it's pretty easy to get a forward slash instead of a backslash, or an asterisk instead of a plus somewhere in the logic, and have the thing misoperate. On the other side, the actual relay failures and malfunctions, you can see that the rate of failures for electromechanical relays is fairly substantial. And I think the comparison between electromechanical and microprocessor here is important, because this is being 2013, 2014, and the bulk electric system, that's the system above 100 kV. There were far more microprocessor relays in service than electromechanical relays. So you can't really compare the relay failures and malfunctions between the two classes directly. Likewise, the solid state relays, just they had such a bad reputation and such poor performance over the years that there aren't very many of them left on the bulk electric system. They're still around here and there, but definitely the minority. So starting out with electromechanical relay testing. Electromechanical relays first started around the turn of the last century. By about mid-1920s, some of you that have been around a little while may remember people talking about silent sentinels, which is the model name for Westinghouse protective relays at the time. They call them silent sentinels, and if you ever see the manual, I can actually, oh, maybe I can't. Let's see. So here's a friend of mine that collects these kind of things. This is the actual manual. This is application guide, and this one was received in 1928. And those of you you can see the kind of flowery writing, half application guide, half product manual. And this was in 1920. And if you go through this manual, you'll find that they had a fairly complete library of protective devices pretty far back. Mid 1920s, they had most all the functions that we have today. Protective relay evolution was kind of slow after that. Through the 1950s, really only incremental changes were made. This shows here an electromechanical relay panel. This was at a incinerator plant project I did a long time ago. You can see that they actually have some digital relays down here over in the corner. Those 4 devices there on that one relay panel replace this entire was it 6 panels worth of electromechanical relays. So you can see that the attraction to the digital protection, and of course they have a modern DCS system there as well. On the right, this is a SR51 multi-amp, one of the first purpose-built protective relay test sets, kind of around 1950s or so. This one actually had an upgraded digital display, so that would put this one in use somewhere around the mid 70s when the LED timers came in. Before that, they had an analog electromechanical stopwatch that measured the trip time. So you can see that the testing was a bit more complex, but the testing itself really grew out of the requirements of commissioning electromechanical relays, and also the capabilities of the relay test equipment that was available at that time. Basic objective of electromechanical relay testing: verify proper operation of relay equipment through inspection, cleaning, exercise, and adjustment. I can admit that when I started in the business, that we were doing a fair number of these. So I guess that's there's obviously a pickup test, so you apply a stimulus and measure the point at which the mechanism begins to operate. Then we had a timing test where you made a pre-fault condition and made a step change in input and measured the amount of time it takes for the relay to respond. Those are the basic tests that we would run on all devices. But because of the special construction of each electromechanical protective relay, there's frequently some special tests that had to be done too, where you would put in a certain input and measure a voltage at a certain point in the relay and adjust resistors or other components in order to get the desired results. So there was not only a standard pickup and time delay test, but there was also some hardware specific test as well. Here we got a little later implementation of the purpose-built test set, and here on the right, this is a variac and load box set up for testing an impedance relay, probably from the 50s and 60s time frame. But as you can probably imagine, hooking these things up to electromechanical relays, it's basically an entire table worth of stuff. It's the level of knowledge that was required to be able to set these things up and test them and adjust these things and get them back into service is admirable, especially without the modern tools that we have today, but you can imagine, relay techs back in the day, you're part watchmaker, part electrician, part engineer to get these things actually working. I talked about that hardware specific test. There were some other tests, reset time test, and then of course carrier communications equipment that would have to be tested pretty much separately because they're a separate box in the panel. And then of course the wiring test. And this aisle there, let's see where, I don't remember exactly where that was, but I took that picture at some point during my field career. You can see the electromechanical relay panel. So the wires from the going to and from the CTs, PTs, and breakers come in here to what we call the field terminal blocks along the edge here, and then the relays are mounted in the panel, and then you have some switchboard wire that goes from the terminal blocks there onto the back of the relay. So electromechanical relays were the only game in town, probably from around the 1900 to late 60s, early 70s, depending on who you ask and whether a relay is introduced or widely used or whatever. At some point, though, we had solid state transistor logic relays were introduced to the market. And here's a good example here that looks like a GE sync check relay, solid state sync check relay. And this is typical of circuit boards at the time. You'll notice, contrary to modern boards that are a kind of a dark green color, which indicates it's what we call a masked board. Those masked board, the traces are actually inside the board, so it makes them very resistant to weather conditions. These early ones, however, you can tell you have the silver traces that are visible here on the board. These are what's called etched boards, and they use acid to etch the board and then dip them, and then the traces would stick to the etched portion of the board, and that's what created the circuits. Bad thing is over time, in a hot, humid, or dirt environment with wide temperature changes, just about like what you'd find in a relay room, the traces actually fall off the board eventually. So these first generation of relays after electromechanical, the solid state relays, had a pretty bad reputation for reliability. Also, one of the issues that they had was there were no testing standards for electromagnetic interference. And I remember back in the day, you go in a substation house and there would be a sign there to turn off your radio because if you walked up to the relay and keyed the mic on the radio, the EMF from the radio would actually interact with the electronics in the solid state relay and cause it to misoperate. So all those things kind of together, in the late 70s, maybe in the 80s, the IEEE Power System Relay Committee brought out a bunch of standards called C3790, C3790.1.2. Those relays set hardware standards for electromagnetic immunity, electromagnetic emissions, HIPOT, which is basically a high voltage dielectric test, and SWC, which was a fast transient test, kind of simulating a lightning strike in the yard. But those standards, and also temperature requirements, humidity requirements, all those hardware standards came about after these electromechanical relays did so poorly, and that really, as an experiment in themselves, electromechanical relays, they really paved the way for the digital relays, because when the digital relays came online, all those standards were already in place. So right from the start, actually, the digital relays were far more reliable than the previous solid state relays. versus maintenance testing for electromechanical solid state and even the hybrid and the first generation digital relays were we call hybrid relays. They usually had an analog back end and then a pretty rudimentary microcontroller on the front end handling the output contacts and the settings and the trip and the communication stuff. So they were kind of half and half solid state, half digital. That's what we mean by hybrid. For any of these devices, because you have specific functions that are tied to specific components in the device, the commissioning test and periodic maintenance test are really the same. We would go through and whether you're putting the relay in for the first time, you run through all of the testing that was in the manual, and then at that time anyway, every 3 years was a typical time frame. You would retest the relays, and you'd run basically exact same test again because each one of those functions had individual components, and of course there's no self-monitoring or anything like that on these. So testing at that time was pretty labor intensive. At the time also there was not much in the way of any automated testing. So all these were done by hands, and you can imagine to do a panel like this, you'd be looking at a couple of weeks worth of work with that old equipment. Following that, again, depending on who you ask, who the first digital relay was, I know that Beckwith had one, I think, in the very early 80s. Pride Relay, I know GE had a line of digital relays. I know the European manufacturers, ABB, had one also very early on. But the digital relay, of course, completely revolutionized the industry, reducing cost, increasing speed, better security, and better near-term reliability. Notice I said near-term reliability because, the electromechanical relays, it wasn't unusual for me to go out in the field back in the day and see a relay that had been in service for 50 years. I don't think anybody thinks that you can put an SEL whatever in anywhere and expect it to last for 50 years. It's just probably not going to do it for just a electrolytic capacitor life alone. But back in the day, that was certainly more the normal. So how do these things work? And we talked maybe a little bit about solid state and how electromechanical relays work, but digital relay really works in a very different way. And here's a block diagram. This one's quite old. This is late 1990s, early 2000s block diagram of a Beckwith relay at this time. But even a brand new one, the block diagram really isn't all that much different on these. And on the left here, you can see we have the voltage and current input. So from the system, we have, depending on where you live, 1 amp or 5 amp nominal CTs. Secondaries, they come into the back of the relay at 1 amp or 5 amp, and then it gets stepped down inside. Usually on the bottom of the relay, you'll see there's a bunch of CTs and PTs in there, and they get stepped down to like the millivolt level. And then there's a low pass filter. Low pass filter basically clips off all the harmonics above a certain point to prevent aliasing. I'm not going to get into that here, but in any case, it helps the relay properly measure voltages and currents. And then the next item in the block diagram here is a multiplexer, and a multiplexer basically serially puts these lines on the programmable gain amplifier and the digital converter. So every time the relay samples, so in this particular case, this relay sampled 16 times a cycle. So about every millisecond at 60 hertz, this relay sampled all of the inputs. So it would put VA on the line, it would measure VA, then put VB on the line, measure VB, and so forth. It would measure all of the currents every millisecond. When it puts a line on, the multiplexer puts a line on the amplifier here. Back in these days, the ADD converters, there was a limitation for the resolution. So in this case, it's 14-bit ADD converter. So what that means is that some relay functions measured secondary current in milliamps. Some other relay functions measured secondary current in the 240 amp range. So that represents obviously a huge range of values you have to measure. So what the relay did was the designer of the relay, actually a guy named Dr. Yawa, he came up with this idea for a programmable gain amplifier. And what the gain amplifier is if we're doing a calculation for reverse power where we're looking at a millivolt test, it would use a high gain. And if we're doing a test for, say, instantaneous overcurrent set at 240 amps, they would use a low gain so that the amplitude of the current coming into the ADD converter was in range. Once it goes to ADD converter, as you can probably imagine, it gets converted to a digital signal. It goes to a DSP, which is really nothing more than a computer that specializes in math operations. And you can thank missile technology and cell phones and everything else for the advances in digital signal processing technology, still done this way. DSPs are typically programmed in assembler. So think like the beginning of, during the Matrix movie, basically people are looking at literally values in hex. And all you can do is add two hex numbers together. And somehow or another, they were able to do discrete Fourier transforms and all kinds of complex math within that DSP just by adding to the contents of two registers together, which is an amazing. It still blows my mind that there are people that can do that. Then we have a dual port RAM, and all a dual port RAM is it's a memory chip that has two inputs, one on each side. The ADD converter the digital signal processor can put values in the dual port RAM, and then the host processor on the other side can read them. Host processor can put values in the dual port RAM, and the DSP can read them, and so forth. So that's a way to pass information back and forth between the DSP and the host processor. Obviously, on the other side, you see the host processor. This is the processor that's usually programmed in C. It does all of the output, the binary output channels, so the trip outputs for a protective relay. Also measures the status inputs, like breaker position that comes into a relay, or a communication, or even a panel switch input that comes into a relay. So the host processor handles all that. Also, any of the digital communications, so 61850, UCA, DMP, even Modbus. Back in these days, it was Modbus mostly in plants, but it handled those communication. Then you have all the supporting pieces: address bus, data bus, memory chips, a flash ROM where the relays programmed is stored, HMI, display, power supply, all the rest of that stuff kind of supporting. Key thing here, though, is that in this particular device, you'll notice there are no parts in there for, say, the undervoltage pickup. We have signal acquisition parts we can collect, and we collect the voltage, but that comparison to the setting is actually done here in the DSP. So we feed the voltages in, and the DSP, kind of like your pocket calculator, crunches the numbers and compares the numbers and generates an output. Yes, I'm above the pickup, or no, I'm not above the pickup, and tells the host processor if the host processor needs to do anything. So this really should have dramatically affected how protective relays were tested, but it did. The industry kind of kept right along testing the way they've always been testing, and kind of ignored the fact that these new devices work in a completely different way. A lot is mentioned. I thought I should probably mention self-diagnostics. And then a lot of relay manufacturers, they talk a lot about their self-diagnostics, and I remember even a long time ago, the self-diagnostics were quite extensive. And just as an example, in the Beckwith, there were two test channels here, a reference channel, which was a maximum input, and a ground channel, which was a minimum input. So every time the relay sampled all these inputs, it tested the reference channel and the ground input. If those were out of spec, the relay would take itself out of service and close the diagnostic content, tell us something, hey, I'm broke. and it's basically a daisy chain of devices. The ADV converter has to stay online. It's also a compute. It's a microcontroller in that as well. Also, the DSP has to toggle a bit to the host processor every clock cycle to tell the host processor it's still running. And then there's a watchdog chip that watches the host processor and makes sure the host processor is still running, and monitors the critical voltages on the board, called VCC. So if the voltage at the board went to an unsafe level, the watchdog would put the processor in reset, hold, make sure the relay didn't misoperate if the battery went dead. Station battery that was powering the relays goes dead. We don't want the program pointer in the relay to lose its place and start executing lines of code that it's not supposed to. So the relays are designed to have a orderly startup and an orderly shutdown. Voltage goes to unsafe level. The watchdog shuts the device down before anything bad can happen. And then when the relay is started up, it has an orderly startup. You'll see most relays, when you start them up, you'll see it clicks and whirs and does its self-diagnostic routine to start up. And part of that is loading the operating code from the flash into the host, and then booting the DSP, and everything goes online in a certain sequence. And once everything is done, the program is released and it starts executing, and the relay OK light turns on, and you're actually protecting. So this self-diagnostic, it comes into play when they discuss PRC 005. It also comes into play when people design their protection testing programs. Some of the things that the self-diagnostics still cannot monitor really is the status inputs and breaker positions that come into the relay, which are now used pretty extensively in logic. Output contact, it can't detect if output contact is welded or failed. And most of these relays use a pretty light duty electromechanical contact. There's some solid state as well, but those relays were selected because of their high operating speed and small footprint and small power consumption and all that. They were not really designed to handle a lot of current. So sometimes if they're misapplied, or if there's a miswire somewhere, they can be pretty easily damaged. Self-diagnostics cannot monitor the metering. So if there's a problem in this low pass filter, which is basically an LC filter, or in the magnetics in the bottom of the relay, we can't see it. And also, of course, self-diagnostics cannot verify that the settings are correct for the application. On the positive side, there are no mechanical adjustments. So the watchmaker part of being a relay tech, it kind of went away. But now you got a laptop and you have these settings. And now, of course, the settings software it started out pretty simple, and it's steadily increased in complexity. This is one from a long time ago, but now if you look at ABB's software for their RED 670 or any of the RE 670 family relays, the software is quite complex and not very super intuitive, but of course very powerful. Program logic actually was introduced. I think in North America anyway, SEL came out. I think 351. This programmable logic example here is I kind of keep it as a joke because I remember back when I started testing digital relays, I was thinking that this was complex logic. And those of you that know now, if you look at a modern SEL device with nested SVs and automation logic, you can have pages and pages and pages of Boolean logic, and even some of the other ones. ABB has a graphical logic now, so I kind of kept it as a joke because I used to think this was complicated, but like so many other things, definitely definitely not complicated by today's standards. So here, for those of you that don't know, this is a trip equation. So any of these um, uh, relay word bits, what we call the individual elements within a relay, assert, then that would assert this trip equation, and the trip equation is mapped to a physical output. So output, say 101, has TR1 in it. So basically, whenever we get the negative sequence time over current element here, the 46Q2T, when that asserts, TR1 goes to 1, and then when TR1 goes to 1, then it's going to fire the output, right? So this is basically the way this works. In SEL logic, the plus is an OR, and the multiply symbol is an AND. So here you can see a SEL logic variable equation where you have an undervoltage element here. It's ANDed with a breaker position and also ANDed with a NOT loss protection. So in order to operate this SV6, and you'll probably see SV6 here, there's SV6 in the trip equation. You go to SV6, this is what's in SV6. So in order for SV6 to assert, you have to be above the pickup of the 27. The breaker has to be closed, and you cannot have a loss of potential situation. And then SV6 asserts. SV6 asserts here, TR1 asserts, and when TR1 asserts, whatever output's programmed to assert when TR1 asserts, the relay trips. So quick, for those of you that don't know, this kind of how SEL logic works. The other complication is on all these relays now support multiple functions, multiple phases, multiple stages in many of these functions. So this is an example here of a digital generator protective relay. All of these numbers are ANSI protection numbers. So 21 is phase distance, 50 is phase over current, 40 is loss of field. So all of these different function numbers. Some of these, say the 21 actually has 3 zones and 3 phases. So this one little circle here would take the place of 3 electromechanical, GBCY, whatever the electromechanical distance relays were. I think the GCY, I think. So each circle here represents more than just one function. So 50, we have 3 different phases and sometimes multiple levels of 50 element that you can set, so forth. So you can see this particular relay has, I don't know, 20-something functions, but really as far as the total protective functions, probably approach 100 different functions. And they're all mapped to different voltage and current inputs on the relay. So testing has gotten a bit more complex as far as testing a multifunction relay. So digital relay testing, taking into account how they fail and the technology that we have, the old standard here, verifying the proper operation of relay equipment through inspection, cleaning, whatever, that really doesn't fit the technology anymore. Now we have additional requirements or different requirements. Verify the I/O is intact. Verify the elements connect to the breaker. And it sounds silly, but you would be surprised at how many times I go out to test a relay and find that there's something wrong with the trip equation, something wrong with the mapping, and the breaker doesn't open when the relay trips. No good. Verify the relay elements enabled. I know of one instance in particular that stands out in my mind where there was a transmission line that was stretching over a Walmart parking lot, and one night the line failed. The line burned down into the Walmart parking lot. Thankfully, it was the middle of the night; no one was there. But the reason is that one phase of phase distance was disabled, and it had been disabled for years. The relay had gone through a number of different testing cycles and been retested, but each time they downloaded the settings of the relay, tested the relay against those settings, Nobody ever really looked at the settings and what was in there, and didn't notice that that the phase distance was disabled. Verifying the settings are correct for the application. This is also a big one, and as relays become more complex with programmable logic and binary inputs and communication, peer-to-peer communication, this becomes more and more difficult. Also, verify the program logic operates as intended. A lot of those things we saw earlier in the SV there, where I have an under voltage element that's supervised by breaker position and loss potential blocking logic. Any asterisk instead of a plus or whatever in that logic equation can cause a relay to either operate when it's not supposed to, or not operate, or operate when it's not supposed to, or not operate when it is supposed to. Commissioning versus maintenance testing for digital relays is also different, because once a relay is commissioned, the settings haven't really changed, or is self-diagnostic to monitor for a lot of this stuff. So you don't have to do quite as much testing on the routine side. But the commissioning testing, because what used to be hardwired in the panel, electromechanical relays, with panel switches and putting relays in series or whatever to construct your logic with hard wires, now is done inside the box. So the commissioning task on digital relays is a bit more complex and a bit more time consuming. So those are the kind of considerations that really should be taken into account. Maintenance test on a digital relay. So this is after it's installed periodically. Right now, PRC 005 on an unmonitored device on the bulk electric system. It has to be retested every 6 years. So that's the standard, and they don't care if somebody was on vacation or you had an outage or whatever, that you didn't get to something on time. I think the fine last I heard, it was $5,000 per device per day, is the fine for a device that's out of compliance. So it's serious business. And these maintenance tests have to absolutely be done. The good thing is on digital relay, the maintenance test is a bit simpler. We check to make sure the relay powers up, download any error codes, download the oscillography, do a metering check, IO check, make sure the output contact trips, verify the settings, and of course you can do some of those with functional tests, or do additional function tests depending on what your test plan is. Commissioning tests really should be repeated when the relay is repaired, or when you change the physical connections, or material changes to the firmware is made. And like everything else, like your laptop and phone and whatever, these relays, the more complicated they get and the more interconnected they get, the more frequent these firmware patches will have to be made. Commissioning test, of course, a bit more complex. All of the previous maintenance tests plus functional testing, which can be quite complex. As far as relay testing currently, there's two different approaches currently used. One is we call it function-based testing, and the other is called system-based testing. Let's talk a little bit about what this is. What is function-based testing? Remember that single line I had with all of the different protective functions on it. Function-based testing is I somehow isolate the output of that particular function. I provide a test stimulus for that function and measure the relay's response. In order to measure the relay's response, I have to kind of create a model of that particular relay. So if I'm testing, say, an overcurrent element within my testing software, I have to tell the software, okay, this is SEL U3 curve, the pickup is 6 amps, and the time dial is 2.5. From this information, the testing software will then construct a model for how this relay should behave based on different test stimulus. Then I proceed, I select my test stimulus, I run my test, measure the relay's response, and compare the relay's response to the model that I created to make sure that the relay passed. Trouble is, if I try to do a pickup test, you'll notice on that single line diagram with all those different functions here, we have, in this case, we just got a bunch of different functions here on this one input. So if I apply current, I'm also, when I'm trying to test my 21, my time over current elements can also operate. My line differential could operate, etc. So I have to have some way of intelligently isolating that. Also, I have to satisfy my logic breaker position, all those other things. So here's an example from what we call our test object, which is a way we kind of create a model of the system. This is a distance element. This is our test object for a distance element. So here we put in the line impedances, and you go to the zone settings and you put in the relay protective element zones. Once you get done with that, then you execute your test, pick your test points, and the software will automatically grade the relay's response. Now, of course, back in the day when I first got started testing digital relays, there wasn't much in the way of this. So you had to create the model in your head and come up with the stimulus and the anticipated response, and do all that yourself, which was obviously much more time consuming. We had lots of Excel spreadsheets to automatically calculate a lot of these values for us. And as you can probably imagine, some of the test stimulus that we were using at the time was not terribly realistic. We would apply balanced three-phase voltage and one current, or do an impedance relay or something like that. Typical way of doing it. So we did it more in a way to make the simplify the testing rather than verify that the relay was actually set in a way that it was going to actually work. So as I've kind of alluded to, the existing methods really don't address that incorrect settings and logic and design that misoperation reports really highlights, right? Those are responsible for a third of the misoperations. And if you test this in a really traditional way, unless you're extraordinarily careful, use different sources other than the relay settings for your test to build your test, and test all the decision points and the logic independently, which is a lot of extra work. You're not going to do a very good job of detecting incorrect settings, logic, and design. You can tell, from the misoperation report, the industry doesn't do a very good job of that, at least at this particular point in time. Another big change that's happening, when digital relays first came out, digital relays had to more or less copy the functionality of the previous electromechanical relay. So when you had a 51 element in a digital relay from 20 years ago, that function really had to operate like an old CO or an IAC electromechanical relay. And I remember when I was at Beckwith, we actually digitized the CO operating curve, humps, bumps, and discontinuities included, to make this digital relay act exactly like the electromechanical relay that it was replacing. Within the last 10 years or so, that has completely changed. Relay manufacturers customers are comfortable with them enough with them now. Relay manufacturers do not necessarily have to follow those old functional definitions. So I just recently had a call from a customer where they wanted to have second harmonic restraint on an overcurrent relay. This was an industrial plant with downstream transformers. So when they energized the transformer, they didn't want the feeder overcurrent to operate. And with a modern digital relay, pretty simple to do. I just, go in the SEL logic equation and write the equation, and there I created this new function. Problem is that nobody's protected relay setting software knows how to do that. So you end up having to create something manually or do something yourself rather than use the automations that are built into the test software. Second thing is relays are becoming more complex. We're really venturing into some uncharted territory. Big one right now is time domain protection. So up until pretty recently, all protection is based on what we call phasers. So we basically have voltages, secondary currents. We calculate the RMS, so the 60 hertz component of that waveform and the angle of that, and we compare that to the settings, and we make a trip decision. These new relays, the SEL T401 is a good example. We're not actually using this phaser quantities anymore. We're actually using a transition from pre-fault to fault in something called incremental quantity. So more complex calculation. The problem is you can't test it with traditional function-based relay. You have to test it with full simulation because you have to hold the source impedance constant when you transition from pre-fault to fault, etc. So there are some challenges that are coming along based on how smart these relays are becoming. I mentioned before, we started doing testing. It was not necessarily the test stimulus we used were not necessarily realistic, and it didn't have to be at the time to verify the element operated. But these new relays are getting smart enough. They know when something doesn't make sense, and the relay isn't actually going to operate the way you expect. Talked about that one. And then at the bottom here, devices and schemes will become increasingly communication dependent. So as these devices become more sophisticated and communication dependent, you have to not only simulate voltage and currents to the device, you also have to simulate any communication, incoming communication with the device in order for the test of that particular function. And this is becoming obviously more and more common. The alternative to function-based testing is something called system-based testing. And system-based testing is instead of modeling the relay, what we do is we model the power system. So here we take we create a single line diagram of the power system, and the software uses full simulation to develop the voltage and current signals. So now we create faults on our diagram. The software then calculates the proper realistic inputs, and we verify the relay's response that way. So in this case, we treat the relay, instead of treating the system like a black box, we kind of treat the relay like a black box, and we simulate the different system conditions to that black box and make sure that the box has the proper output. So this is really kind of much better oriented toward testing and how relays actually fail in the field. Handles communication, test complexity does not increase with relay complexity. So as you can imagine, with really, really simple relays, creating the model of the system is more work. But as we get these more sophisticated devices, at some point the seesaw balances the other way, and it becomes easier to model the system than to try to model all of the nuances in the protective relays algorithm. So comparing the two methods, we have function-based testing here and system-based testing, and then here's back to our coming full circle here with our NERC misoperation study, and you can see how well each method handles the potential misoperations that are reported to NERC. And here you can see pretty clearly system-based testing does a better job, and especially as the relays get more sophisticated, this difference actually gets bigger. So what's next? What's kind of gone from the past to the present? Now let's looking at the future. IEC 61850, the digital substation that you probably hear about or read about. I've been hearing about it since around 2000 or so. I think I saw Dr. Alex Apostolon give a talk on it and decided I would never have to learn it. But a couple of years ago, I realized I wasn't going to make it. And SEL as one company resisted it pretty strongly um, for for 20 years. And then 2 years ago, Ed Schweitzer came in. I think it was at Western Protective Relay Conference, and he announced that SEL was going to be the number one provider in 6150 based solutions. And here in just a couple of years, I just took the screenshot of last week, and I went on the SEL website and I searched for 61850. And now you see 1,200 results, 106 products, 996 documents, 14 videos. I don't know what education is, 8 classes, maybe eight classes for 61850. So hopefully everyone watching this can look at these statistics and see this is not going away this time. And if you want to be in this business over the longer term, you're going to have to become familiar with 61850. So what in the world did I have this old clip here? From what was 1963. Somebody said you'll be able to carry a phone. It took a while, but I think we made it there. This is kind of an example of how technology is frequently forecast. But anyway, what in the world is this digital substation stuff? So here's a traditional substation where I have CTs and PTs and copper cable going in through a test block and going to my individual relays. If I'm going to test this, I open up my test block, I plug in a test paddle. This is where I'm going to inject my test set voltages and currents back into my relay and verify the relay's response. So relays, binary inputs and outputs also go back through a test block. And I can provide a stimulus through the test block to the relay and measure the relay's response through the test block. Pretty simple, right? Too bad it's all going away. So for a digital substation, to give you kind of an idea what all that means, we've got a couple different iterations here. The first iteration here is we have something called merging units. And merging units basically a fancy way of saying a digital relay out in a cubicle somewhere. It's going to measure the voltages and currents and read the breaker position and issue trip and close commands as the system orders them. And it lives out in the cubicle. It's just going to be a aluminum box most of the time. And then going back in the substation, instead of all this copper, what we're going to have is we're going to have one Ethernet cable. It's going to plug into a network. In this case, this is the process bus, and this is going to be read. All the values are going to be read by any protected device that's programmed to listen to them. So you are not going to have all those miles of copper, CT and PT and input and output wires anymore. You're just going to have Ethernet going to a switch, and then each protected device plugged in a switch. On the other side, there's another Ethernet network where all the binary IOs go out. We have a PTP network, high precision clock. We have communication with the control center. We have engineering that's be able to query these and get reports on misoperations. So here you can imagine, what if a relay misoperates over the weekend. Have an automated system where the engineer comes in on Monday morning. He's got a work list, and here he sees this operation. He clicks on this operation. He downloads all the oscillography data and looks at the settings. And this you can imagine the labor savings of having an automated system like this compared to the old way, where everything was papers and radios, how things were actually reported. So the possibilities are endless. So how does this 61850 thing work? If you don't really remember much else, it has 4 different parts. It has a client server part, a goose part, sample value part, and then a network part. And there's three different services. So Goose message obviously you can read it there, genetic object oriented substation event. It's actually a digital version of those binary inputs and outputs, those hardwired breaker positions or trip and close commands, whatever that we used to have going around in copper in a substation. Now they're going by Goose command, and that's real time, it's high speed. The other services, and one of the other services, sample values. Sample values is instead of sampling the voltages and currents and doing an AV converter at the relay, what we do is we do all that at the merging unit, and then we send a sample value stream. So basically a stream of voltage and current samples, put that on the network, and any device that's interested can subscribe to that stream and use that stream in a trip decision down in their time coordinated high speed real time sample value stream of samples. And then finally, on the other side there, you see client server. Client service is just like it sounds. It's kind of like you have a client and you have a server. So say the control center can make a query to a device, and device answers. Control center can issue a command, tell a breaker to close. That will be done via client server. So 3 different services, 4 different parts. This is the basic structure of 6150. If you're in this business, I recommend get on YouTube and watch a few getting started with 61850 videos. We put out Omicron. We put out a bunch. There's a bunch from a bunch of different sources, but I would encourage you to take a look and get fluent at least with the terminology and what's going to be coming. So testing 61850 substation is a bit more complex. What we got, right? So here we don't have test switches. We can use a conventional analog input and output, but here this shows kind of what our offerings are. This is our same services, Goose, sample value, client server. So we use our CMC test set. Instead of pushing voltage and currents and measuring binary inputs and outputs on the front, we plug in an Ethernet plug, and we can push sample value streams. We use our same software, same everything, but just instead of pushing analog values out the front, it's pushing sample values out the back. And then we measure Goose. We provide a stimulus to the relay. When the relay responds with a Goose message, we can read that Goose message and grade that relay response just like we did in the old days. So that part of it is still works the same way. It's just the channel is different. And of course, because it's an Ethernet-based solution, we've got some other tools here. We got IED Scout, which is basically a software that sniffs the network. You can look at any device on the network and see what's happening on the network, what Goose messages are present, what client server communication is done, and so forth. The SV Scout, another software, Deneo. We have a software that will measure sample value streams, so you can actually plug in the network, subscribe to sample value stream, and you can see a calculated RMS value. This allows you to troubleshoot these networks. Obviously, if the network's pretty small, maybe not so hard to test, but you can imagine a major substation that's fully digital. You could literally have dozens of merging units and dozens of relays and a very complex network topology that you're gonna have to make it work. So you'll need different tools and different skills to test these new devices. And I think that's my last slide. I know we're about out of time, so past a little past time. Are there any questions?
We do have a few questions, Scott, and
okay.
One of the ones that came up late in the discussion was regarding cybersecurity, and is it ever going to reach a point where you could depend on security using a network-based system?
That's a great question. And the answer is the first rule in any cybersecurity thing is there's no such thing as a secure system, right? That's first rule, but we do have mitigation. We actually have a product. It's called Station Guard, and there will be a flood of products. And most of the difference between say your laptop and a station, these networks are designed from a permissive standpoint. So you're only allowed to do what the framework is set to let you do. So only the devices that are supposed to be talking to other devices can actually do that. Whereas, your laptop is completely different. It's actually inverted. It lets you do everything except for a list of things that you can't do. So the structure of the network is completely different. But that's not to say, I think that in the end they'll be pretty resistant to we'll say casual hackers, but state actors, I would imagine. I know United States, we hacked into the Iranian the centrifuge is a big, pretty well known hack. Years ago, the utilities in Ukraine were hacked. The operating network was penetrated, and they were able to shut the system down. There was also the Aurora project where the Department of Energy ran an experiment to see if you could damage a generator remotely, and they proved that you actually could by opening and closing the breaker rapidly a number of times. So the threat is certainly there. It's definitely being addressed. You can see that now with utilities. They have SIP requirements. Now you have the ropes, and at some point I suspect that test technicians and people of the company are not going to be able to plug their laptop computer into the operating network. You're going to have some sort of firewall in between the two. And again, these systems are designed from a permissive standpoint, so that only the allowed operation, only the designated operations are going to be allowed, and everything else is going to be blocked, which is, like I said, fundamentally different from the architecture of other computer systems or networks.
So we've run long. There's a few questions we haven't been able to get to. We'll do a Q&A response that we can have downloaded when we post the video. Scott, thank you for a very good job. It's really excellent information.
Okay, I'm glad everybody glad you liked it, and I'll look forward to hearing from everyone.
So long.
Bye.